So welcome back, everyone. So Christmas is coming closer, but we still have two more lectures today and on Thursday. I hope still some people will show up on Thursday, even though it's just one day before Christmas, but we'll see. Okay, so where did we stop last time? We were considered with so-called orthogonal expansions. Yeah, so we started with an orthonormal system. Yeah, so an orthonormal system is a sequence of elements in a pre-Hilbert space where you check the scalar product of pairs, and if the vectors are not the same, it should be 0, and if they are the same, it should be 1. Yeah, so like these are vectors of length 1 that are orthogonal to each other, or vectors of functions, since we are in an arbitrary Hilbert space. And we checked a bunch of properties of such orthogonal systems. And the first thing that we noticed was the so-called best approximation property of the Fourier coefficients. So if you compare any element in our vector space with this linear combination of elements in our orthonormal system, and these xk are the Fourier coefficients, so that means I didn't write this here. Xk is the scalar product of x and ek. Then we get this representation for the error that we are making with this approximation. And if we use any other coefficients, yeah, so we replace now the Fourier coefficients by any arbitrary coefficients, then we are making the same error plus the deviation from the Fourier coefficients. So that means we get the optimal approximation of an x with our orthonormal system if we use the Fourier coefficients. Yeah, that's a direct consequence of these two equalities here. And so the first equality we can further refine. Yeah, we did this in Bessel's inequality. Since we know that the left-hand side is a norm, so it's definitely non-negative, we can conclude that this here, the sum of the squared coefficients, has to be smaller than the norm, which is the first part. And we get equality here, so that the norm is equal to the sum of the squared coefficients if and only if the error that we are making is 0. And the same holds true if we have infinitely many elements in our orthonormal system. Yeah. The series of the squared coefficients is still bounded by the squared norm, and we get equality here in this inequality if and only if the approximation error is 0. It's just that we have to look at this approximation error in a slightly different manner, because you're like summing infinitely many elements in an arbitrary Hilbert space, and yeah, for this we just look at the limit of this difference and not at the limit of this function here directly. But from this limit being 0, we can directly see that this sum here converges in the norm to our element. That means we can represent this here by an infinite linear combination. And with a finite linear combination, we come arbitrarily close if we have equality here. And this is what led us to define when an orthonormal system is complete. Yeah, complete in the sense that it can represent any element. And this is now if the norm of all elements squared equals the sum of the squared Fourier coefficients. Yeah, that's like a quite indirect definition, since this doesn't immediately say that we have to be able to approximate these x with our orthonormal system, but knowing this connection here, it's hopefully getting clear why we made this definition. Yeah? This here, no, if we have that the limit here is 0, then we know that this sum converges in the norm to x. Yeah, it converges in the norm to x. But so without this condition here, so without the equality here, we do not know what this sum is doing. Yeah. Yeah, and to refine the interpretation of this definition of a complete orthonormal system, we also characterized it in the following way, and this was the last thing we did in the last lecture. So an ONS is complete if and only if for any element and any accuracy we find a finite number of elements in our orthonormal system with corresponding coefficients, so that we get to our x with distance at most epsilon. So we get arbitrarily close with a finite linear combination of our orthonormal system. Yeah, that characterizes the completeness. Yeah, and that's where we stopped during the last lecture. And now I want to make one final of these more general statements in arbitrary Hilbert spaces before we go to the Fourier series. And this is the so-called Parseval's identity. And again, we are in the very same setting as before. So we have a normed vector space with scalar product. So a pre-Hilbert space. And a complete orthonormal system. Yeah, and here I only explicitly consider the case that the orthonormal system has infinitely many elements, because it's obvious that this holds for finitely many elements. So then we have that we can represent the scalar product of two elements x and y in our space X as the series of the product of the Fourier coefficients, where the second one has to be conjugated. Yeah, so you can think of this as a generalization that we can represent the norm in the complete orthonormal system as the sum of the squared coefficients. Yeah, we can represent the scalar product as the infinite sum of the product of the real coefficients. Or you can also think of this as the C infinity scalar product of the Fourier coefficients of x with Fourier coefficients of y. And why is this the case? So I'm using the same notation as before. That means that xk is the case Fourier coefficients for x, and yk is the case Fourier coefficient for y. So, and the first thing that we have to show is that this series here is actually well defined. Yeah, so that we have convergence of the series. Otherwise, we cannot handle this object. Yeah, and so for this, we just look at the partial sum. So we check what is happening if we only sum up to element k. And additionally, we look at the absolute value here of the elements that we are summing, knowing that if the absolute values converge, then we have absolute convergence of this entire series. Yeah, so and now I somehow need to bound this. And yeah, so there's not so much that I know. We just know that x and y are in X. So which would mean that since the orthonormal system is complete, we know that the norm is finite since we have an element, and we know that this infinite sum is finite. So do you have any idea how we can connect the knowledge that this is finite to the need of bounding this from above? So what would be like the typical trick to separate such products? There are not so many named inequalities that we have at our disposal from linear algebra. Yes, we can use Cauchy-Schwarz. This is like Cauchy-Schwarz for the complex scalar product. Yeah, we apply this and get the product of the squared coefficients of x, and from this the square root, and the same for y. Yk, of course. Yeah, so just applying Cauchy-Schwarz, we get this upper bound, but we also know that these two series will only get bigger if I sum to infinity. Yeah, so this is smaller equal to the full sum to infinity, but we can also go a different route and use directly Bessel's inequality. Then I don't have to go to the limit and can just directly bound it with the squared norm. Yeah, so this is now the norm of, not the two norm, the norm in our space times the squared norm of y, and that's smaller than infinity. So in particular, this bound here is independent of k. So we know that this series of absolute values has to converge. Yeah, it is increasing and bounded, so convergent, and that means the entire series is absolutely convergent. So the series without the absolute value. Yeah, so that means we now know that the right-hand side exists, and we still have to show the equality here. And we will show the equality for the real and the imaginary part separately. So the claimed equality for the real part and the imaginary part separately. And first, we note that if we have the norm squared of the sum of x and y, we can write this as scalar product of x plus y with itself. And then we can multiply everything out. And we used this trick before. Yeah, so just multiplying everything. And if I change the order, I get x, y conjugated. So this is x norm square. This is y norm square. I just accidentally wrote x there. But if I add xy plus xy conjugated, this is 2 times the real part of xy. And we call this star. Now let's just note that the Fourier coefficients are linear. So in the following sense, if I add the Fourier coefficient for x and y, both for index k, I have these two scalar products, but there I can use the linearity of the scalar product, and this then is the k's Fourier coefficient of x plus y. And with this, we get the following. And probably I should first sketch the idea. So we know how to represent this, since we know that we can represent the squared norm as sum of the squared coefficients. We also know the same for these two. And that means if we have these three things, we get a representation for the remaining part. So the real part of the scalar product that we're looking for. Yeah? So this is why this equation gives us a way to represent the missing scalar product. So we use that we have a complete orthonormal system to replace the squared norm by the squared Fourier coefficients. Now I use the linearity of the Fourier coefficients to split this x plus y k's coefficient into k's coefficient of x and k's coefficient of y. Yeah, now I can factor the square out and get xk squared plus yk squared plus 2 times real part of xk times yk conjugated. Yeah, that's like the equivalent of a plus b square for the complex absolute value. Yeah, and you get this exactly like we got this equality here. Yeah, since we can write this as scalar product of xk and yk. So this scalar product in C. So now again we use this is a complete orthonormal system. To see that this is the norm of x squared. Oops. This is the norm of y squared. And this is what is left over. And for the real part, I can just pull it out of the series. Yeah, we already know that this converges, so we know that all of the objects here converge, or that all of the objects exist. Yeah, this we showed before. Yeah, so we have that this is absolutely convergent. So that shows that we have this. And from this, we can conclude that also this series here has to, or no, that this series has to converge. Yeah, since some of converging series are also convergent series. Okay, and this means we are pretty much done. Because let's look back at star. So we have this representation for x plus y norm squared. And now we have a different representation for x plus y norm squared. So that means these two things are the same. But since these objects share x norm square and y norm square, we can just cancel them. And we can conclude that these two objects are the same. So we have that the real part of x and y is equal to the real part of this series, which is like half of what we wanted to show. Yeah, we have now shown this equality just for the real part. But fortunately, we can use simple argument to also conclude the equality for the imaginary part. Yeah, since we have that the real part of I times z for any complex number z is minus the imaginary part of z. So we just need to replace x by ix. Yeah, so we have shown this here for arbitrary x and y, so I can just insert ix instead of x. And do the same computation again, and we get that minus the imaginary part of x and y is equal to minus the imaginary part of this sum or the series. Yeah, and that's all we needed to show for Parseval's identity. Yeah, and as announced, this concludes this arbitrary, this general part that is just working in abstract pre-Hilbert spaces. And we come now back to our problem of computing the Fourier transform on an actual image where images are given on bounded domains, not on all of RD. Yeah, so the Fourier transform, we spend a lot of time understanding how it works, but we need it to be on all of RD. Yeah, and it gives us for an L2 function on all of RD another L2 function on all of RD. That is this frequency domain representation. But now we only, or we want to restrict this on functions that are given on hyperrectangles. So rectangles in 2D, for instance, exactly how images would be. So images are typically given on bounded hyperrectangles. Yeah, and this is just a fancy word for this tensor product of intervals. Yeah, and the typical use case for us is just a rectangle or the unit square when we think about images. So so we are interested in a transform that is not on all of RD, but on such hyperrectangles. Yeah, and we want to transform like the Fourier transform. Yeah, and I think we briefly already discussed this last week. Your first idea, of course, could be to simply extend your image with 0. Yeah, because it would be no problem to extend an image from the hyperrectangle to the to all of RD. But then the problem is that the Fourier transform of this extended image lives on all of RD. Yeah, and so it covers a much bigger domain than we started with. And we want to avoid this. So we don't want to have like an over representation of our images. We want a precise representation. And of course, it's always the easiest to consider the 1D case. And the special case that the interval is symmetric. This makes life a little simpler. But it doesn't really restrict us, because with scaling and translation, this can be generalized to arbitrary intervals. Generalized to intervals with scaling and translation. Yeah, these are simple transforms that we could combine with the transform that we create. And then with the tensor product to hyper rectangles in any dimension. Hyper rectangles in any. Yeah, so this is a very nice property of these hyper rectangles, that they are just a product of intervals. Yeah, for instance, unlike a circle, which cannot be decomposed into the product of two 1D objects. Another benefit of these finite domains is that we can directly use L2 functions. Yeah, so this Fourier transform integrals, we needed to start with L1, since the classical way of defining the Fourier transform does not work for L2 functions. Yeah, we needed a lot of time to fix that, but this is not a problem on the bounded domain. Yeah, and first we define a scalar product, because of course the reason I inserted this orthogonal expansion chapter or section is that we need it now. And since we have been using pre-Hilbert spaces there everywhere, the first thing we need is a pre-Hilbert space, which is why we need to define a scalar product now. So, and we define the normalized scalar product as follows. Scalar product of f and g. And here I indicate the interval where the functions are defined. And it's pretty much like the scalar product on L2. The only difference is the scaling factor. Yeah, that I'm here normalizing by the length of my interval minus b to b. Yeah, it just changes the scaling. And now we will see why I use this scaling. We can now look at the functions ek with k and z. Given by ek of x is e ikx. Yeah, so these are the functions essentially that we used in the Fourier transform. Yeah, since the Fourier transform was integrating f times e to the minus I x omega. So x is still here. Omega is now replaced by k. And these functions are actually an orthonormal basis of L2. So of L2 minus pi pi with respect to the scalar product that we just defined. Yeah, and that we divide here by the length of the interval makes these functions also normal. Otherwise, they would just be orthogonal, and we would still have some scaling factor here to make sure that they integrate to 1. Yeah, and that's like moved to our scalar product definition. Yeah, and orthonormal basis, this was just another word for complete orthonormal system. Yeah, I defined this last time. So that means with our known complex exponentials, we can use all the nice things that an orthonormal basis can do. So I don't want to prove this in detail here, just some remarks on how you do this. So the orthonormality is easy. So that this scalar product of EI and EJ is delta IJ. You can just easily compute. And I actually plan to do this in the exercise session on Friday, but we didn't have time to do this anymore in the end. But it's like 2 or 3 lines of computation. It's just integrating this product of complex exponentials. So that's not the difficult part. The difficult part is the completeness. Yeah, so for the completeness, just to recall, we need to show this equality of norm to sum of squared coefficients. But this is nothing that you can easily show directly. So it's better to go this way. So to show for any element that you can approximate it with a finite linear combination in arbitrarily well in your norm. And this is how you do this also for the complex exponential functions. And there you have just to combine 2 well-known statements. So the basis property can be shown using corollary 340. So the one that I just that we just recalled, 344. the Weierstrass approximation theorem for trigonometric polynomials. Together with the denseness of the continuous functions in L2. Yeah, so of C, the continuous functions on the interval minus pi pi with complex values in L2 minus pi pi C. So there are some more details on this in the book of Bredis and Lorenz, and I put the reference in the lecture notes if you are interested. But just to roughly see how this is done. So we want to use this 344. So that means we start with an L2 function and this epsilon bound. Then we first approximate this L2 function with a continuous function, like with error epsilon half, which we can do by the denseness of C in L2. And then we approximate this continuous function with the trigonometric polynomial with the Weierstrass approximation theorem. Yeah, because this is what Weierstrass says, that for any continuous functions, you can find a trigonometric polynomial to get arbitrarily close to that continuous function. Yeah, and these two steps combined, we get the desired approximation here. Good. And one thing to note here is that I'm indexing these over the integer numbers, so all positive and negative integers. And in the chapter before, we used the natural numbers for indexing. Yeah, so this may look different, but since we have absolute convergence, we can just re-index the integers with n and use all the results from section 3.2. So we can re-index z with n. Yeah, to use the results from section 3.2, our orthogonal expansion. Since we had this absolute convergence of the of all these series, and absolute convergence implies unconditional convergence. Convergence. incomplete spaces, and L2 is complete. Yeah, so to index Z with n, you could just, for instance, start 0, 1, -1, 2, -2, and so on. Yeah, so you just need to hit all the integers by going through all the natural numbers. So, and if we now can use all the results from section 3.2, we can in particularly use this basis property. Which we also call the completeness. We get that this f in L2 minus pi pi to the complex numbers can be expressed as series so sum over k in Z, f scalar product with ek minus pi pi ek. Yeah, so this is just using the completeness, and here so we have to be careful what the equality means. So where the equality is to be understood as convergence of the series in the L2 norm. Yeah, so let's go back here. Yeah, so we said our orthogonal system is complete if this is equal. Yeah, and we showed that or at least I referenced that our complex exponentials form a complete orthonormal system. So that means we do have this equality, which means we do have this equality. So that shows that the series of the orthonormal system elements scaled by the Fourier coefficients converges in the L2 norm to the elements that we're representing. And this is how this equality has to be understood. Yeah, so this converges to an L2 function, and in the sense of L2 functions, these are the same. So this does not mean that the pointwise evaluation of this here converges as series. So let's explicitly write this. I don't have it in the notes, but I think it doesn't hurt to stress it. Yeah, so I could just check the evaluation here and then check what the series is. But this is not what this means. Yeah, so we have no real control of what the individual point evaluations of this series do. Yeah, so this has to be understood as a linear combination of L2 functions, and this, in the sense of L2 functions, is converging. Okay. So just means you need to be careful not to look at this object, so really at the evaluation, and there the series. Okay, and yeah, this was just a side note. So the series here that we have is now called Fourier series. And the coefficients this is 1 over 2 pi integral minus pi f of x e to the minus I kx dx are the Fourier coefficients from definition 336. Yeah, there I just defined that the scalar product of our element with any orthogonal basis element or orthogonal system element is called Fourier coefficient. And now we see hopefully the relation where this why this is called Fourier coefficient. And we used here that eikx conjugated is e to the minus ikx. Yeah, because if you insert f and ek in the definition of the scalar product, we have to integrate the product of f with the conjugate of ek, and ek was defined without a minus, and the conjugation here gives us the minus. And yeah, if you now look at this Fourier, yeah, please. Okay, no, and if you now look at this Fourier coefficients, you can actually see that it coincides with the Fourier transform. So except for some different scaling factor here, if f would be extended to all of Rd with 0, and this omega is just an integer and not an arbitrary frequency. Yeah, so that means to represent functions on bounded intervals, it is fine to look at countably infinitely many frequencies where we needed uncountably many frequencies for the case where f was defined on all of Rd. Yeah, there we had to really integrate over all these over all of x, and no, and in the this is like the inverse, integrate over all the frequencies. And here we drastically reduced this to just countably many coefficients that we need. Yeah, so we change this from z to n because you need the positive and negative integers in here, and it's more convenient to index the positive and negative integers with z instead of like having an extra mapping that does this for starting on n. But I thought that in the beginning, so when you start getting exposed to these orthonormal systems, it's more natural to just start counting. Yeah, so you start with one and then you go on, and it's quite unnatural to start with zero and then count in both directions. But it's equivalent due to the unconditional convergence. Yeah. Yeah, so in this sense, you can see that there's a very strong connection to the Fourier transform. And yeah, and this here now then looks more or less like the inversion formula, because you get back f from the coefficients. Yeah, so the coefficients, they look like the normal the frequencies obtained by the Fourier transform. Yeah, and they are done with integration, but the inversion is done with this countable sum. So yeah. No, so no, we get to a different domain. So from RD we got to RD, and now from an interval we get to Z. So these look very different. So you give a function, and the transform then is a sequence of coefficients. Yes, infinite, but countably, and not uncountably. So that's the difference between Aleph 0 and Aleph 1. Or like the difference between the rational and real numbers. Yeah, so natural numbers, integer numbers, and rational numbers, they are like the same amount. You can index each with each other. But the real numbers, they are more. Yeah, you cannot index the real numbers with with the rational numbers or the natural numbers. Like a different kind of infinity. No, so for images on bounded intervals, we need countably infinite many. So there, yeah, this continuous thing cannot be fully represented by a finite amount of coefficients. Do you mean the discrete Fourier transform? No, the discrete Fourier transform gets countably many and gets finitely many and returns finitely many. Yeah, you start with n coefficients and you get back n coefficients with the discrete transform. But the Fourier series is not discrete yet. Yeah, so we are just like halfway there. We first restricted our domain from RD to a interval or to a hyperrectangle. Yeah, which is more realistic or more close to our image case, because we when we do think of an image, we only have like a partial view of reality, right? It's not that we could make a picture of everything. But there we do not have to discrete the pixels yet. Yeah, we can just look at like the continuous version without discretization. And this is the state where we are. And with the realization that the Fourier transform really needs much fewer like coefficients to work there when we restrict our domain. Yeah, but we are not discrete yet. So, and now that we have this new, or this concept of Fourier series, we should compute a Fourier series so that we can see how a function is transformed into a set of coefficients. But before I look at this first example, let me note that we can just transform any symmetric interval to minus pi pi. Yeah, because what I have said here was specifically for minus pi pi, but we can easily transform this to minus b as follows. So we can look at phi b that transforms minus pi pi to minus b, and x is mapped to b divided by pi divided by x. So just a simple rescaling. Yeah, this brings us the divided by pi brings us to minus 1, 1, and multiplying by b then scales minus 1, 1 to minus b. So this can be generalized to L2 of minus b for any b bigger 0. And then the complete orthonormal system is just slightly changed exactly by this transform. EKB of x is EIK pi divided by b x. Yeah, just this simple rescaling here is enough to transform the orthonormal system from minus pi to minus b. Okay. So let's have a look at a rather simple function. So f from minus pi pi to r, and x is mapped to x times pi minus absolute value of x. Yeah, almost like a polynomial. We just have this extra absolute value in there. Yeah, so if we want to think about this, yeah, at 0, this is 0, and so if we would multiply out, we would have x pi minus x times norm x, and x times norm x is like x square, except that the negative numbers stay negative. So instead of like a parabola like this, it would look like this. So it should, so this thing should look roughly like that. So, and let's Yeah, of course, with another 0. So this, yeah, this was not a very good drawing, because of this has 2 zeros at 0 and at pi. Yeah, so no, somewhat like, no, somewhat like this. So if we put in positive number, no. Okay, no, sorry, no, it's like this. Yeah, if x is positive and smaller than pi, this is positive and this is negative. Positive, so it's both positive. X is smaller than pi, so that means on the right hand side it has to look like this. But if x is negative, this is negative, but this stays positive since we have the absolute value here, so it has to look like this. So a little bit like how a sine or how a sine would look like. So, but now let's compute the Fourier series of this. So, and first we note if we insert minus x, so f of minus x is minus f of x, since the absolute value here just removes this minus. So that means f is an odd function, yeah, which helps us simplifying the integral. So f is odd. Yeah, and to compute the Fourier series, we need to compute all the Fourier coefficients. So all the integrals of f with e to the minus ik. So integral from minus by pi, f of x, e to the minus I kx dx. Yeah, now we use the usual Euler formula that we always use to compute this kind of integrals. And then we can just integrate real and imaginary part separately. Now just a tiny bit of reordering. So that's f of x times cosine k of x, yeah, because cosine minus k of x is the same as cosine k of x, minus I divided by 2 pi, yeah, pulling out this and using that minus sinus kx is minus sinus kx is sine of minus kx. Yeah, sine is odd, like f is. So here we have integral minus pi f of x sine k of x. So, and so I mentioned that this is odd. So what is this? Odd, even, or nothing? Yes, this is odd. And what's about this? Yes, it's even. And what is the integral over an odd function over a symmetric domain? Yes, this is 0. So we don't have to compute any of this. And what is the integral of an even function over symmetric domain? Yes, 2 times the integral over half. So that means I can get rid of the 2 here. So they have minus I divided by P, integral minus pi, 0 pi, 0 pi f of x and now if I insert the definition of x, you can see that using the evenness of the integral and halving the integration domain lets us get rid of the absolute value, which makes our life much easier. Because since we are on the interval 0 pi, we know that the absolute value of x is the same as x. So we just have x pi minus x squared sine k of x dx. Yeah, this we now have to compute. Let's forget about the scaling here for now, so that I have less to write. And yeah, integrating this we do by integration by parts. Since if we do this twice, this second order polynomial will be gone, and we can always easily integrate sine and cosine. So this is x pi minus x squared minus 1 over k cosine kx. It's bound 0 and pi. And now we have the derivative of this, which is pi minus 2x. Yeah, and still like the integral of this, which I already put there, which is minus 1 over k cosine kx. But so what happens if I insert 0 or pi? So if I put 0 here, I get 0. If I put pi here, I get pi square minus pi square, which is also 0. So this entire first part is just 0. And we can continue with this. Minus times minus gives us a plus. Oops. I can take out the 1 over k. Integral 0 to pi minus 2x cosine kx dx. Yeah, and here we just split this into 2 integrals. The first one, pi over k, integral 0 to pi cosine kx. And the second one, minus 2 over k, integral 0 to pi x cosine kx. Yeah, so again, simple integration. Yeah, integrating cosine, we already did that. That's, I know we integrated sine, but integrated cosine is same. So it's 1 over k sine kx. with the k we already have. It's pi over k square sine kx 0 pi minus 2 divided by k. Yeah, here we do integration by parts again. Yeah, x we keep, and integral of cosine kx is 1 over k sine kx. Bounds are 0 and pi, minus integral from 0 to pi. Derivative of x is 1, and the integral of the cosine again 1 over k sine kx. Yeah, so you can easily read the brackets. Yeah, sine at multiples of pi is 0. So this is 0. And this is also 0. So we are just left with minus 2k 1 over k square cosine kx. Yeah, and now we can collect everything. That's 2 divided by k cubed. So cosine of k pi is minus 1 to the k. And cosine of 0 is 1. So, and this means we are pretty much done. We can simply recall that we had yeah, this is what we wanted to have, and it was minus I over pi times this integral, and the integral we just computed. So I get exactly this minus I divided by pi times what we got for the integral. Yeah, and we can see that the minus and minus is cancels. And now we can make this even a little bit shorter. If we look at the case that k is odd, yeah, if k is odd, minus 1 to the k is just minus 1, and minus 1 is minus 2. So we get minus I divided by pi 4 over k cubed. And if k is even, minus 1 to the k is just 1. 1 minus 1 is 0. Yeah, so this means we we have computed the full, all the Fourier coefficients, and we can represent now, yeah, this continuous function, which looks roughly like this, as sum of over Fourier coefficients like here. Yeah, in this manner. And we turned out we only even need half of these coefficients, only the odd ones, not even ones. Okay, and Now we have also all the tools to show an important theorem. That tells us how to sample functions that only have a certain bandwidth. Yeah, this is a very famous theorem and something that you definitely should remember. So it's called sampling theorem, or also Shannon-Whittaker theorem. So what does this say? So this is more from signal processing rather than image processing, but still it has some important consequences for us. So we look at an L2 function with limited bandwidth. What does this mean? That means if we look at the Fourier coefficients, they are 0 if the frequency is bigger than b in absolute value. Yeah, so we look at the function where the Fourier transform like lives in a big circle. Everything outside is 0. Yeah, which means there are like no very high frequencies, and b is the bound. Which, for instance, is the case after you have applied a low pass filter. Then you know that your signal has bounded frequency. So, and what can we say if this is the case? Some very interesting things I would claim. Then this f is continuous. Yeah, so even we start in L2, this boundedness of the frequencies gives us actually continuity. Of course, since we're in L2, being continuous means it has a continuous representative. And is uniquely determined by countably many values. F of k times pi divided by b, k and z. And moreover, so not only know that we only need these countably many values, we also know how exactly we can evaluate f. So it's the series over all k in z, f of k pi divided by b. So these are the values that I claimed are the uniquely determined as f. And we have to multiply them with a certain cardinal sign, scaled and shifted according to these frequencies. Yeah, so we are given an L2 function with limited bandwidth, and it turns out that we only need to know f at certain positions to get the entire f back. Yeah, which is very important, for instance, if you think about recording signals. Yeah, if you do some recording, like every X milliseconds, you record a sample. If you think about time-dependent signal, yeah, if you know what the bandwidth of the signal that you're recording is, you know how often you have to record, or every how many milliseconds you have to record to get exactly the signal, so that you know that if you record fewer samples than you need, that you do not have all information, but that also that recording more samples will not give you anything more, that the information is already completely contained in these star samples. Yes? One application is also that there are hardware low-pass filters, so that you can like build a low-pass filter that is before your recording, and this would allow you to perfectly record the signal up to a certain frequency. Yeah, if you combine such a hardware low-pass filter with this sampling theorem knowledge. Yes, so you can think of f, if you have the real numbers as origin, as time. Yeah, and any time-dependent signal, of course, you cannot record all values at once, like you would do with a picture. Yeah, when you make one picture, you just get all the values at a certain time. But if there's a time-dependent signal, for instance, somebody speaking, then you must, of course, record these samples one after another. Yeah, since they depend on time, and yeah, this tells you what the distance in time between your measurements has to be to get the entire information, so that you don't sample more than necessary, or that you don't get more than well, the test, so if you do processing, hardware processing to get bandwidth limits, so this is how you could get this B, for instance. Yeah, then it tells you what the sampling pattern is. Okay, so we will see this in more detail next time, and probably it's just some visual impression of this, and I will come back to that next week. So this sign has a limited bandwidth, and you can see if I just take these, if I take the values at the axis, I can easily represent the sign. But if I take the values at the dots, I get a completely wrong impression. So the dots are the case if I take less samples than Shannon-Whittaker tells me. And we can see it really leads to something that's undesired. And the axis is what we do if we take more samples than Shannon-Whittaker tells us. But we will look more at this effect in the next lecture on Thursday. Yeah, and that's all I wanted to tell for today.